Okay.
Okay.
Okay, cool. So yeah, today I decided to go on the Gnosis Safe. It's pretty interesting in it because quite a few, I've heard of the Gnosis Safe MultiSig quite a lot. It seems to be quite hyped up. So yeah, there's all these pretty famous names use it. So I was just curious to go into it and see what it was like. But what I didn't realize before starting and what I just learned an hour ago from going to the AMA that Akun posted was that those been around for quite a long time. Like apparently they started like in really early days of Ethereum, and they were initially part of Consensus, and then they spun out their independent thing. So it's a lot more it's pretty deeply rooted. And so yeah, basically I think Gnosis has multiple products. Their first product was the prediction market, and they've got more products going on now. So I think they're also behind CowSwap as well, and Gnosis Chain. But what I wanted to focus on today was just the Gnosis Safe MultiSig Wallet. So it's a set of smart contracts which works as a multi-sig wallet. And I guess you're pretty familiar with this, but just some basics to hash over. There's the single private key wallet that we're pretty familiar with. And then so instead in this multi-sig wallet, you basically have several owners. So in this diagram, you have 3 owners, and you need M of N confirmations for each transaction to go through. So in this case, someone can propose a transaction, and then out of the 3 owners, you need 2 people to sign that transaction before the transaction can go through, be approved, and be executed. So just some quick reasons why multi-sig wallet. So single private key, if you have a single signature wallet, vulnerable if you have one private key that's compromised. For an individual, it can be more secure to have several private keys. So you can lose one, or if you get attacked, then you can give that private key up and not compromise, I guess, the security of that multi-sig wallet. And for teams, you can have multiple team members sign every transaction. So I thought this was an interesting clip to watch. So they have this clip that takes 60 seconds just to set up Gnosis Wallet up. I don't think this has sound, but yeah, this is pretty much the Gnosis UI on how to create a wallet. It's only 60 seconds, so it shouldn't take too long. I also don't know why the resolution here is that bad. It wasn't that bad when I tried to look at it. But yeah, you see the guy putting in the 2 wallet safe owners. And that's the team safe, and then just some more parts of the UI. And yeah, so that's pretty much how the multi-sig wallet looks from the front end. So one other interesting thing is that they performed formal verification of their contracts. So it's something I haven't heard of before, but apparently it's a way that they can mathematically verify that the contract works as intended. I won't go into the details, but from what I read, it was very time intensive. There's a link here if you want to go into further detail. And so some of the components of the Gnosis Safe, so there's the UI, there's smart contracts, there's the API to store signatures and apps to do extra functions. And so I was going to focus on the smart contracts part. And so pretty much this is what I think is the bread and butter core flow. So you have the proxy factory. It's one contract. You call create proxy on it, and then it'll create a proxy and each sort of multi-sig wallet has its own proxy. And then the interesting thing is that in the create proxy function also calls the setup function in the same transaction. So create proxy, it creates the proxy contract as well as does the setup. And so I'll go a bit more into detail on this later on, but so what happens after that is the team or person who has a multi-sig wallet, if they ever want to do a transaction from the wallet, they then call exec_transaction on the proxy, and that makes a call to GnosisSafe here, and that calls the contract. So essentially, there's one proxy contract, one proxy factory contract. Each team has their own proxy contract, and there's one GnosisSafe contract. That's a logic contract. And so, yeah, so proxy factory contract, it provides a simple way to create the proxy contract that points to the master copy. So the master copy in this case is the GnosisSafe. That's if you're familiar with the proxy pattern where there's a proxy contract that points to a logic contract, and you can upgrade the logic contract by redeploying the logic contract and pointing it to somewhere else. That happens in this pattern, but there's an extra element of the proxy factory, which I'll go more into later on. But yeah, basically proxy factory, it creates the proxy contract, and the proxy contract points to the master copy of the GnosisSafe contract. And in the same transaction, you'll execute this function to do the setup function, which initializes the proxy contract state. So basically this whole create proxy setup, it all happens in one transaction. And so one thing I wanted to go over so one pattern that they're using here is the minimal proxy contract pattern. So essentially what happens here is you have one proxy factory and you have one logic contract here. And you can basically make as many proxies as you want. And so the advantage of using this pattern is that it's pretty expensive to create a contract by itself. But if you use this pattern here, it becomes cheap, and each proxy is basically a clone of each other. It becomes very cheap to deploy clones. So it's basically is like a factory, because you're just making mass-produced proxies, and each proxy points to the single master copy. They have several terms which I think all mean the same thing. So master copy, singleton, logic contract, implementation contract. In the Gnosis system, it's all the GnosisSafe contract. And then, so two benefits here are, so like the proxy pattern that we're familiar with, it lets us upgrade the contract logic by updating the address of the master copy, and it also enables cheap deployment. So that's the two main benefits of this pattern. So then Proxy.sol, it actually only has a constructor and a fallback function, and the fallback function will just delegate call to GnosisSafe. The GnosisSafe contains the logic, and then the proxy contract actually has the tokens on it, and that's the storage state. So, and then Gnosis is pretty much where all the core logic is. There's quite a lot of functions to it, but I thought for my own sanity and to limit the scope, I was only going to focus on these two functions here: setup, which sets up the initial state, and exec_transaction, which executes transactions. But even with just these two functions, you'll see that there's quite a lot to it. So, and another pattern they use is inheritance. So the GnosisSafe contract, it inherits all the contracts, so OwnerManager, ModuleManager, fallback manager. I'll go into more detail on them later on, but they basically contain different parts of logic, which I guess it's a modular design. And GnosisSafe setup, and I'll just show you what I mean when I was talking about the contracts before. So this is the proxy factory here. And so essentially the main function here is create proxy. This is interesting because I think they have the GnosisSafe proxy contract. The singleton address is just the GnosisSafe contract address, and they somehow create a new GnosisSafe proxy contract object just here. And I think in the same line, the address of this proxy also gets assigned. And then here, essentially they make a call. This is basically making a call to this newly deployed contract with the data that you put into this function is the call data or transaction data for this call. And this will revert if that call reverts. So just something that's just a really good resource that I found helpful for this was this website here. And if you find the call, yeah. So basically it will return 0 if the subcontext reverted 1 otherwise. So essentially this whole thing will revert if this call to proxy will revert. And then looking at safe proxy. So yeah, basically just the constructor function. And then this fallback function. The main part of this fallback function is this part here, where it makes this delegate call to the logic function. And then that's the main part of it. But I guess I was looking into the other parts because I couldn't help but look into it. But this part here, if you're sort of interested in the rundown of what's going on there, I spent some time sort of digging into it like here. So basically like what happens in this line here is, this is probably a bit too much to get into, but you're basically, and you can, yeah, I just thought leave it for your own time to read this if you're interested. Basically like if you're calling master copy, then as your call data, then it just basically returns the singleton address. That's what this part does. Then this part's basically copying your call data to memory, and then your call data becomes the delegate call data. So yeah, that's basically a delegate call. Then here, let me see what I wrote for that. Okay, you basically return the data from your delegate call here, and then you basically revert if that delegate call reverted, and then you just return your data here. So that's a GnosisSafe proxy. And then the actual GnosisSafe contract, yeah, basically this is all the inheritance that it does. But I only focus on this one here. And if I go to the setup function here, so yeah, first is setup owners. And so this was in OwnerManager here. And that was, so that's basically this function here. Let me see what else I wrote. So yeah, OwnerManager, it basically has these functions. It adds, removes, and replaces the owners. And you can view the list of owners. So add, remove, and replace so this is setting up the owners. This is adding owners, removing owners, swapping it. You can also view and change the threshold number of owners. So change the threshold, get your threshold, is this person owner, and then get owners. Oh, and the main thing that I was really confused at when looking at this first, that I haven't seen before is the data structure that they use to store the addresses is, so I guess if I got this question of if I wanted to store a list of addresses, what would I do? I guess my first answer would be a dynamic array of addresses. So I'd go something like address. I've got the exact syntax, but basically like a dynamic array. But what they do here instead is they use this mapping here. And essentially you have this situation and this is what the mapping looks like here. If you if you have A, B, and C as the owners, your mapping basically looks like this. So this address 0x1 equals A, owners A equals B, owners B equals C, owners C equals 0x1. I think address 0x1 is just this arbitrary sort of extra link that they put in there to sort of maintain this circle. And it's I haven't seen it before. It's interesting because it's actually pretty convenient in that, so you can check if someone's an owner or not, because if this owners of your address is 0, then they're not a current owner. So say, where is owner? So basically, if the owner isn't the Sentinel owners, and if yeah, so basically, the owner can't be the sentinel owner, and you can't have the address 0 as a result of that mapping. I'll leave it to your own time to run through how they sort of set up that mapping here, because it's pretty easy to sort of, I got mixed up the first time when I this is where they set up that mapping, but I got mixed up the first time when they set it up. But basically, if you put in A, B, and C, this is your sort of result data structure. And sort of I guess what's next? Okay, so I guess the advantage of doing this is that I found this interesting because you basically have of one to add and remove addresses. Whereas with a dynamic array, like if you want to insert an element into the middle of the array, like you have to shuffle all the elements in front plus one array, and you have to reallocate. So there's like, if you have an array of 10 and you put something in the first index, insert something, then you have to move 9 elements now. Whereas with the linked list, you just have to basically just change, where is it? You just have to change this value. You just have to change 2 mappings every single time you add an address or remove an address. So it's more, I guess, gas efficient that way. And the other thing is, so the other operations on the linked list are, so it's O of 1 to check if the address is owner, because if the address is the result of putting address into owner 0, then it's 0. And then it's O of n to iterate over the list of owners, which is the same as a dynamic array. So I guess it's a sort of unusual data structure, but I guess the benefit here is that it's basically just changing 2 mappings to, instead of your length of array operations, to add and remove addresses. That's probably the most practical thing that I took away from these contracts. So then you have your fallback manager. It handles the fallback function. The documentation says that it's required to make the safe compatible with the ERC 721 token standard. So if I go there, this is the internal set fallback handler that is basically here. And so basically all they're doing this is just setting the storage slot for this handler. I guess I haven't seen this before where they manually set the storage slots. They manually found the storage, they manually have a storage slot that they chose for this, to put this in. And I guess technically that's more gas efficient, but practically you probably don't need to do that in a simple contract. Like you could probably just have address fallback manager equals and then this is like Solidity sort of manually setting the storage address for you, and you don't have to worry about what the actual storage slot is. But I guess they've chosen to manually deal with the actual storage slot number. So that's the fallback. Oh, yeah. Was there a question? So it's just, I guess it's what they've called their function, but I guess the fallback handler is the same thing as the fallback manager.
Okay.
So it's basically saying that it's to manage fallback calls to this contract. So that is the fallback manager. And then setup modules is in the, so I wrote that here as well. It's in the module manager. And so the modules are smart contracts, which add additional functionality to contracts while separating module logic from the core contract. So basic safe does not require any modules. Adding or removing a module requires a confirmation from owners. Modules can include daily spending allowances, amounts that can be spent without approval of other owners. Modules enable developers to, I didn't know that this cut off. So what did I write there? So enables developers to include their own features via a separate smart contract. So I didn't really go too much into module manager other than the setup function, but it's basically what it does here is there's some checks. This line is just to make sure that it can't be set up again. And then it's basically making, so this call here, it's basically not a nested call to execute, and it's basically a delegate call. So if you look at what the execute function is, it's in Executor. It's basically this function here. It's basically a way to, it's basically a function wrapper around assembly delegate call or call. And so next is, so basically making a specified delegate call to set up the module. And I guess you're handling that delegate call in another contract, which I think I was able to trace where it went to. But I guess it's for the individual modules contracts themselves. So next you've got GnosisSafe.handle payment. So that is this function here. It took me a bit to understand what it was doing, but what this function basically does is it sends, you can basically specify to send a payment in ETH or ERC20 to someone else. And I guess why you'd want to do that is, I don't have here, I think I wrote it a bit later, is, yeah, so you can handle the payment of ETH or ERC20 to a specified address. It's optional. So there's this concept of relayers, and relayers can send the transaction and pay the ETH gas fee for you. So they can actually call so someone else, so the person who calls this execute transaction function here, it doesn't have to be one of the owners. It can be someone else. It can be and that someone else is a relayer, because all this exec transaction needs, and I'll get onto this later on, is it just needs to write signatures from the owners, but anyone can actually send the transaction itself with the right signatures. And so to sort of enable that, they pretty much encode this functionality to sort of pay someone to handle payment. So basically, I think the idea is the relayer will either call the setup function or the exec transaction function, and they'll encode these parameters for themselves. And hopefully that's in agreement with whoever the wallet's being set up for. And so they'll sort of set up this transaction to pay back themselves. So that was a bit, so see how we're only one function in, and there's a lot of stuff to unpack just with one function. So that's the setup function there. And then next we'll go into the exec transaction. So that's the second call that I want to cover today. And so that's this function here. And so the first part is the encode transaction data. That is basically this part here. It's basically just, what did I do there? Yeah, it's basically just ABI and putting all the arguments into an ABI encode and then hashing it. That's basically, and then hashing it. And then this part here is basically this is basically the standard for the EIP 712 signature, which, yeah, basically what this function does is it gets an EIP compliant hash of that transaction. And that's to be signed by the MultiSig wallet owners. So next is check signatures. So yeah, so that's basically this part here. And so basically it checks whether the signatures provided are valid. So I guess this is probably the most important security critical part of this whole function. And how they've chosen to store signatures is, so Ethereum signatures are 65 bytes, and they basically concatenate. So if there's 3 signatures, they concatenate that into 195 bytes. So 365 byte signatures side by side. And so basically how you sort of divide 65 byte signatures are, you have a 32 bytes R part, 32 bytes S part, 32 byte 8 UN8 V part, which is 1 byte. That's the ECDSA signature standard. And so if I go to where it cut itself off, they've actually chosen to use a different V variable to mark their own signature types. So what I mean by that is if I go into check signatures, is that, okay. So this is the check signatures function. It basically makes another call to check end signatures, which is this function down here. And there's some more assembly stuff that they do, but this function, so basically you're feeding this function the transaction data, the hash that the EIP712 compliant hash that you made before, and the signatures. So your sort of whole bundle of signatures and the number of signatures that you need. And basically in this for loop, so for each, you're iterating over each signature. First thing you do is you split up the signature into its VRNS component. How they do that, I can quickly go over that. It's in signature decoder. Yeah, so this whole function here is split into split. Basically, they're using assembly to take this bytes and split it up into the R, S, and V component. It's pretty low level operations on how they do that, but they need to do it this way because this V part here is only 1 byte. And so in Ethereum, it stores data in 32-byte chunks. So this R is in one chunk, this R is 32 bytes in one chunk, S is in 32 bytes is in one chunk, but V, it's only 1 byte. So in order to get that, to grab that V, that 1 byte, you basically need to use assembly and bitwise operations to get that. But they get that, and so they split up the VRNS, and then, yeah, interesting part here is they have conditional branches based on what the V is. So if V equals 0, if V equals 1, if V is bigger than 30, else. And so they've used, basically going back to what I said here, is they use different Vs to make their own signature type. So they said that if V is 0, then it's a contract signature. V is a 1, it's approved hash. V is more than 30, it's been adjusted for ETH sign flow or else. And then the default V for Ethereum ECDSA signatures is 27 or 28. If it's not 27 or 28, this function won't return a valid address. I think it just returns a 0 address. And so that's basically this check signatures function here. And then they're just going through to check each signature. They're getting from each type of signature, they're getting the current owner. And they're going through these checks here. So this one's here is to make sure that you don't duplicate the so it's not you're not doing duplicate signatures. Otherwise, that's going to revert. This one here is to this line here is to make sure that a signature, when you get the address that signed the signature, you then get if you have to make sure it's an owner. If it's not an owner, then it returns 0 address. Otherwise, it reverts. And this is just to make sure it's not. This is something implementation detail of the linked list. So that's check and signatures. And next is check transaction. So this function here just pretty much gets the address of the guard, and guard has the check transaction function, but I couldn't actually find a implementation for this check transaction function. So if I go here, this is just an interface. It doesn't have the implementation. This doesn't have check transaction in either. And when I search in the repo, I think they had some examples. Yeah. But I think these are examples and I'm not sure if they're the actual guard. I'm not sure if this is the actual check transaction implementation used on chain, but it seems here that this is a nonce checker. This here is the check, basically guard against reentrancy. So just basic transaction guards like that is the point of, and this part here, they're manually making sure that the gas is above a certain amount, just to make sure, I guess they must have calculated that they needed this amount of gas. And then next part is, so this execute function, this line is basically where the function gets executed. And we visited this function before in this function here. It's basically making this low level call to here. And where are we? Back here. So another sort of programming pattern they used here is that this is all block scoped here. And I guess they made a comment to limit the variable lifetime and prevent stack to deep error. So I guess that's a way around the stack to deep error. And then, oh yeah, so yeah, that's where basically you have all these checks and stuff around it, but that's basically where the whole point of the function happens on one line. And then you're putting more require lines. Yeah, you have this handle payment thing again, which is just sort of letting the transaction executor choose who to pay after the transaction's done. It's an optional thing. And then these are emitting events, and then check after transaction seems to be the same thing as check. Seems to be like a similar thing to check transaction. I couldn't find an implementation, official implementation, but seems like it's, yeah, to guard against things like replay attacks and reentrancy. So yeah, this is basically put the diagram again to show, this is basically what we covered is create proxy setup that happens in one flow and exec transaction. There's a lot more to the GnosisSafe system, but I was just gonna cover these calls here. Yeah, and some takeaways is there's lots of assembly. It's very gas optimized, but I think for most, I think there's probably no point in being gas optimized if it's not for something that's not heavily used, but because it's pretty prone to error. Like the main prime example I can think of is that they manually set a storage slot in the assembly, whereas you can pretty much do that without having to worry about the storage slot number, just using normal solidity. They use the linked list to store a dynamic list of the owners. There's something else here that got cut off. Yep, so they're segmented into modules. They use numbered error codes. So if you sort of look at the errors, then it's just GSO13, GSO10. Yeah, bitwise operations to get these data chunks like that 1 byte V portion of the signature, and then block scoping to prevent stack to deep error. So these are some resources which I found helpful to understand what was going on. And then, yeah, these are just appendixes, just sort of my own scratch paper for working out what was happening in the assembly, which I guess I'll leave. Oh yeah, so that's it. It's only 2 functions, but I think it's a big headache just sort of trying to wrap your head around those 2 functions, just those 2 functions.
I think that's a great presentation, and considering that the contract has so many assembly code. Thanks very much.
Oh, no worries, man. No worries. Does anyone have any questions or anything like that?
Anyone on the call has any questions? Actually, I have a.
Go for it, Francis.
Yeah, I have a quick question about GnosisSafe and GnosisSafeL2. Do you know what's the difference?
So it basically inherits it, but I think it's just adding extra functionality. So it's just a new exec transaction function, a new exec from module function. They're basically just adding new functions onto what's already here, because they're basically just saying super.exec transaction and just adding. I think it's like because the GnosisSafe v1 was already used very widely on mainnet, but they just want to make a very minor upgrade and just add something to the function body. So this is what they just added. They're basically just adding this to the function body of exec transaction in the original Gnosis Safe contract.
Okay.
And then the same thing, yeah, they just added a new event basically for this.
Oh, so they just add the emit. Is that
yeah, that's basically what they did in this L2.
Okay.
Yeah, there's basically just adding a few lines to the original GnosisSafe, and then all the core functionality logic is in here. But yeah, there's a lot of things that they inherit in here, so it takes a while to understand step by step what's what they would be doing.
Thank you. Dan, do you have any question?
Hi, is Jefferson still there, or?
Yeah, I'm here. Yeah.
Okay, sorry, I couldn't see you. My internet just broke, and I just had to come back. Thanks a lot for an amazing presentation.
Thank you.
It was really good. I'm quite amazed that they basically implemented everything themselves, right? There's no library calls at all.
Yeah, I think the thinking there is what I'm sort of thinking about is they probably started this before Open Zeppelin was a thing, is my gut feeling.
Yeah.
And the other thing is the guy was saying, I remember on the AMA that the guy was saying that he worked side by side by the people who were making the Ethereum code base in the early days. So that might be another reason why there's not too many imports here.
Okay, yeah, makes sense. I mean, if they really started so early on it, and it's also so highly optimized, you're not really going to get that in a library, I guess.
Yeah. It's pretty. I mean, this is the first time that I really start to get what was going on in assembly. And I guess like the two things that helped me with trying to get my head around it were like, firstly, this resource here, and then in assembly, I was just using this function to basically see what was happening in assembly.
I just wondered if you looked at the upgrade aspect of the contract.
Which upgrade aspect? I didn't go too far into it, but which upgrade aspect?
Is the logic in GnosisSafe upgradable?
Or? No, because, well, it is, because you can redeploy this contract, right? And then if you go to Gnosis Proxy, I'm just wondering, can you actually change this address here? I'm not sure if you can actually.
I wonder if you have to go to the factory, because surely.
Yeah, you have to go to the factory to deploy a new proxy, and then you put in the singleton address, right?
Okay, yeah.
I mean, I guess they had to make this contract as short as possible. So just to make that proxy factory part as cheap as possible.
Yeah.
Mm.
So this looks a lot like the proxy that we looked at last week, right?
Probably does, yeah. Maybe it's a copy.
It's not quite the same. I would need to look a bit more closely. I can't quite see the difference, but it does look very similar.
Yeah, because the thing is that all the work happens in this one line here, this delegate call line, and then they put all this stuff around it, which makes it more tricky to interpret.
Yeah. Certainly the fallback is very similar with the delegate call, which is obviously where like all the magic happens.
I mean, the thing I was thinking was it's probably really dangerous to have a unchecked delegate call. Not that I have it here, but it's just something I was thinking about yesterday, where if you can make any random delegate call, then you can basically delegate call to make a transfer of tokens out of that contract. But I think you can do that with a normal call anyway.
But this delegate call is purely to store the implementation contract, right?
It's to redirect redirect the calls to the implementation contract. Yeah, but I found it interesting that they, in 2 lines here, they create the contract and then they basically, the contract's not even like technically live. Like it wouldn't be live on Etherscan yet, but somehow the contract object exists and you can make a call to it to then make a delegate call. I found that, interesting.
No,
Like,
I think the line 16, when you execute that line, then there will be a new contract deployed on. So then you will have the contract address, right?
But I don't think you can access the contract address until after this call. But I think this function accesses the contract address before the call is finished. So there has to be some in-between state where the contract exists, like within the transaction. But like, I don't know too much about the, that part escapes me. Like, what's the actual ordering of stuff that happens?
Okay. Okay, anyone else have any more questions? If not, I think we will end the session today. Thank you very much to Jefferson for the presentation. Great presentation. Thanks.
No worries. Thanks everyone for coming along. Thanks, Francis, for organizing.
Okay, thank you. We'll end
the slides up on the WhatsApp chat.
Yeah, that's you can also put the link in the meetup. I think there is like a comment session if you want.
Okay, yeah.
Cool. Thanks.
All right, thanks a lot, Jefferson. Thanks, Francis.
Thank you everyone for your participation.
Thank you, guys.
All right. Cheers. See you guys.
Cheers.
Thank you. Bye.
Thank you. Bye.